The square roots. Maybe just under roots, and we'll call it square roots. Square roots. And the reason I like this is because the square root symbol is probably my favorite in all of math to draw. It looks like this. And I'm sure you've seen it before. That is not a division sign. Division signs just look like this. This has that little V shape, whatever shape thing there, looks like a heart monitor where you see the spikes up and down there. Okay. This little sign here is called a radical sign. Okay, and this thing right here is called the radicand, if in case somebody ever asked you. Okay. And I suppose the reason that they throw square roots at you right now is because square roots are like the opposite of exponents. Okay? This is not a division problem in any way. You don't do any division at all to find this. When you're asked to find a square root, what you're asked to answer is this. What same number times itself will give you the radicand? Oh, the radicand. In other words, this. If you want to know what the square root of 16 is, that would be the number that times itself gives you 16. What same number times itself will give you 16? And again, you kind of need to know your multiplication tables on this. Caitlin? 4. The square root of 16 is just the number 4. The square root of 4. What same number times itself will give you 4, Ryan? 2. The square root of 36. What same number gives you, when you multiply by itself, Kayleen? 6. Now let me tell you, while I ask you this question, how about the square root of 10? What same number times itself gives you 10? Brooke? There is not one. Actually, there is, but it's like we get close to it. It's got to be somewhere between 3 and 4, because 3 times 3 is 9, 4 times 4 is 16. We call this in math square roots that don't work out. Maybe this makes sense to you. They're called irrational numbers. They don't make sense, because if you were to take a calculator, and sometime in your life it'll be okay for you to use a calculator for mine, and you type the square root of 10, you will get a decimal number that never ends.
Oh, in pi.
It's a lot like pi. Pi never ends. But square roots that don't work out, okay, never end. We call them irrational because if you know what the word irrational is, it doesn't make sense. And we can't think of a number that has a decimal that never ends, because our minds can't really think about infinity or keep going on forever and ever. But, okay. Now the ones that do work out, and the ones we talked about, for example, the square root of 1, the square root of 4, the square root of 9, the square root of 16, the square root of 25, the square root of 36, the square root of 49, the square root of 64. All of the ones that do work out, every one that does work out, we call those the perfect, I'll find it in here. Where's my square thing? They're the perfect squares. Okay? These are the perfect squares because they work out nicely for us. Okay? But most square roots aren't perfect squares. For now they are for you because the book will only give you those. But, you know, what times what gives you 1? What times what gives you 4? What times what gives you 9? What times what? You know, these are all perfect squares because they work out nicely to nice even numbers. But most, in the real world, most of them won't. You know, you can get close to the answer, but you'll never get exactly the answer per se. Mia? Zero, well, in reality, if you had the square root of 0, it would be 0 because 0 times 0 is 0. Okay, so yeah, you could call that, but other than that, we don't deal with zeros a whole lot in that situation. Cabran?
So does it not have one if it ends with a 0? Like how the number 10? Or
Well, 100 does. 10 times 10 is 100, so 100 would. You can't make a generalization and say if it ends with a 6, it's not going to be a perfect square or whatever. And there's no easy way to do it. You just have to kind of try it. Okay, now to take it one step farther, because they throw a whole lot of stuff at you. Actually, go back to your powers ones. Go back to the exponent one that we just talked about. This one here. Because I have to give you this because the book gives you this. The book is going to ask you this. Let me give you an example here. The book will tell you to write 4,500,000 in expanded form using exponents. And it sounds much more difficult than it is. And I'm sure once you see it, you'll say, oh, that's not so bad. I'm going to leave this up here so we can see it while I do this. See if I can't shrink it a little bit. If you go back when we did this before, 4,500,000, how did we write this in expanded form? Do you remember expanded form? What did we do? We did, Brooke, 4 times 1 million plus 5 times 100,000, right? Well, what will make our life easier is that we can write these numbers as powers of 10 and not have to write all those zeros, just like I talked about here. So instead of writing 1 million, I'm still going to keep the 4, but it's going to be times 10 to the 6th power, because remember I said however many zeros followed is the exponent. So that would be your first part, 4 times 10 to the 6th power, plus 5 times 10 to the what power? How many zeros are in this up here? 5 zeros. So this is right using expanded notation using exponents. You can throw another one at you there. How about this one? 7, 0, 8, 0, 4, 0, 0. If I said write that in write that in expanded notation using exponents, this would be 7 times 10 to what power? Really all you have to do is look at how many digits come after the 7. How many digits come after the 7? 6. That's the power of 10. Plus 8 times 10, and again just look at how many digits come after the 8. 4, and then plus 4 times 10 to the how many digits come after the 10? After the 4? 2. And that is the expanded notation using exponents. Cabran?
So would you just use like 10?
If there was a digit here,
No, would you just use 10?
you're always going to use 10 for the numbers. And the exponent is always going to be over how many digits come after it. Okay. Except for the last digit there. If this was a 6, you go 6 times 1 because it's not times 10. Technically, it's actually 6 times 10 to the 0, but we won't go into that. And the other thing they might give you is a problem that looks like this. The square root of 9 plus 16 compared to the square root of, compared to the square root of 9 plus the square root of 16. In which case, the first thing you would do, Maggie, is to, like paper, carve on your paper, right? let me ask you a question here. What is 9 plus 16? Anybody?
9 plus 6 is
25. And what is the square root of 25?
5.
So you know this side is 5. Square root of 9 is?
3.
Square root of 16 is?
8. Oh, my bad.
What is 3 plus 4?
7.
So which one's bigger? So just in case you see it look like that, you'll be in